Okay, in the last class, we started with coordination chemistry, and we have seen that there can be different kinds of ligands. There can be so-called monodentate ligands that have only one point of attachment, and there can be multidentate ligands that have multiple points of attachments. And we've looked at a few examples of bidentate ligands first, and we have seen that most bidentate ligands form 5 or 6 membered rings with the metal ion, and that is because 5 and 6 membered rings are more stable. So one designs these ligands so that the ligand can form 5 and 6 membered rings with the ion, thereby giving complexes with the greatest stability. So one example is here, in which an oxalate ligand forms 5 membered rings with an iron center. So let us go from the bidentate ligands to the tridentate ligands, just so that you know a few examples of these also. And so one common ligand is the bis-ethylene triamine ligand. It's abbreviated TWIS, so please know these names and also the abbreviations. So in this case, we have 3 nitrogen donor ligands that are separated by 2 ethylene units. So we can see that again when that ligand binds to a transition metal ion, that we are forming 5 membered rings that are very stable. So an aromatic analog of this TWIS ligand is the terpyr ligand or terpyridyl ligand, in which we have 3 pyridyl linkers fused together in a way so that the nitrogen atoms are separated by 2 carbon atoms. And again, this is designed so that the ligand can make 5 membered rings with the transition metal. So here just a couple of examples of tetradentate ligand. So one important ligand is the porphyrin ligand. So the porphyrin ligand has 4 nitrogen donor atoms, which are part of a macrocycle, as shown here. So these porphyrin ligands are biologically very important. For instance, the hemoglobin in blood contains such a porphyrin ligand. We have an iron in the center. Another example is chlorophyll, where you also have such a porphyrin ligand, but you have magnesium in the center. And these porphyrin units that are complex, that are complexating a metal, gives these substances their characteristic color. So that's the reason why chlorophyll is green, and that's the reason why blood is red. So related to that, there's the phthalocyanine ligand. You see here the structural similarities to the porphyrin ligand. The difference is that these carbon atoms here are substituted by nitrogens, and that you have additional phenyl units that are now condensed with the pyrrole units here. So the phthalocyanine is a ligand that is commonly used to produce dyes. So depending on what metal ion you actually place into the center, you can create dyes of various colors. All right. Sorry again. So here's an example of a hexadentate ligand, EDTA, which stands for ethylene diamine tetraacetic acid. So you see here the structural molecule with the donor atoms in red. So you see here, you have here an ethylene diamine unit with 2 nitrogens that are bridged by this ethylene unit here. And then you have 4 acetic acid units, 1, 2, 3, and 4 that are attached to the 2 nitrogens. So ethylene diamine tetraacetic acid acts as a ligand in its deprotonated form, in which these 4 protons are being lost, and that gives then a ligand with a 4 negative charge that can bind to all kinds of metals. So here is illustrated an EDTA complex with calcium plus, and you see that calcium is coordinated by this ligand in an octahedral fashion. So you see here, there are these 2 oxygens that are standing in trans position. Okay. You see here, these 2 nitrogens of the ethylene diamine unit are standing in cis position, and we have 2 remaining oxygen atoms of the 2 remaining acetic acid groups standing also cis position. So overall, you see that this calcium is octahedrally coordinated by these 2 nitrogens and these 1, 2, 3, 4 oxygens. So these EDTA complexes are very stable thermodynamically because the EDTA ligand can attach to the metal ion by 6 points of attachments, and we have overall 6 5-membered rings between the ligand and the metal ion. Okay, so in the next step, let us develop a systematic nomenclature for coordination compounds so that we can talk about coordination compounds in an educated and unambiguous manner. So the first thing that we have to realize is that when we count the number of ligands that are attached to a particular metal ion, then this number is indicated by a Greek prefix, which is placed before the name of the ligand. So when there are 2 ligands, we use the prefix di. When there are 3 ligands, we use the prefix tri. When there are 4, we use the prefix tetra. When we use 5, we use the prefix penta. When we have 6, we use the prefix hexa. When we use 7, then the prefix hepta. When we use 8, the prefix octa, and so forth. So we're not restricted to 8 ligands. You can have 9 and even more, but that number is not so common anymore, just because the associated coordination number at the metal will become extremely high, and it's difficult to fit so many ligands around a particular metal center. And we will talk about this shortly in more detail in this course. Okay, so now how do we systematically name a complex? We distinguish between the nomenclature of anionic complex ion and cationic complex cations. So let us look at the anionic complex anions first. So in this case, you need to name the positive counter ion first, but you do not number the number of positive ions with the Greek prefix. We just name the ion without numbering it. So secondly, you number and name the ligands and you place an O behind the ligand to indicate that the ligand is anionic. So thirdly, you name the metal ion and place an 8 as a suffix behind the name of the metal ion. And after that, you can either place the oxidation number in Roman numerals behind the name, or you place the charge of the anion in parentheses behind the name. So both is possible. So let us do this by one example. So here we have 3K plus FeC and 6 minus. So how do we name this coordination compound? We realize first that it's a complex anion. So we name the positive counter ion first. So this is just potassium. Remember again, we ignore the number of counter cations. So in the next step, we number and name the ligands and place an O as a suffix behind the name of the ligand. So we have here cyanide anions that are coordinating to our metal. How many do we have? Well, we have 1, 2, 3, 4, 5, 6. So therefore we have a hexa cyano fragment in the name. Note that for making pronunciation easier, we call the ligand not a cyanidoligand, but only a cyano ligand. So please remember that. So now we are done with step 2. Now let's go to step 3. We name the metal. And the metal is iron, but when we have a complex anion, we do not use the English name if there is a Latin name for that element. So in this case, there is a Latin name, which is ferrum, and the element symbol is according to that, Fe. Therefore, we use the name ferrum and place the ending 8 after the name. Now again, to make pronunciation easier, we remove the ending um and place the 8 directly between fer, so that gives overall ferrate. This is a general rule also that you need to keep in mind. So when the metal has a Latin name, and then remove the ending and attach the ending 8 directly to the beginning of the name. So last but not least, we either have to add the oxidation number or the charge in parentheses. So what would be the oxidation number? Well, we have to consider that our complex anion has a 3- charge. Yeah. So we have 6 cyano-ligands that are anionic. So we have 6 times 1 negative charge. That gives 6 negative charges. So if you think about what do we have to add to -6 so that we get -3, and the answer is, well, +3. Okay, -6 + 3, that gives -3. We can also put the charge in parentheses behind the name, and that is very easy because we can read the negative charge here. That's a 3-, which we would have to put in parentheses. So overall, that would be either a potassium hexacyanoferrate 3 in Roman numerals, if you want to name the oxidation number. Then we say that this nomenclature is in the so-called stock system, or we call this compound potassium hexacyanoferrate 3-. We call this nomenclature the nomenclature in the Ewing-Bassett system. So you can use either of the two, but you need to know them both, and you have to be able to do them both, and you also need to be able to know to which system the respective nomenclature belongs. Okay, so in an exam, if I ask you, well, do the nomenclature according to the stock system, in this case, don't place a 3- behind, that will cost you points, but you would have to place Roman numerals behind the name. Okay, to indicate the oxidation number. Okay, now let's do a few exercises together. So here we have an H2 PTCl6. Can anybody tell me what would be the correct name of this coordination compound? You may unmute yourself.
Would it be hydrogen hexachloroplatinate?
That's correct. So in the stock system, what would be the Roman numeral for the oxidation number?
4.
4, correct. Yes. In the Ewing-Bassett system, what would be the negative charge at the anion?
-2.
-2, correct. So this is hydrogen hexachloroplatinate 4 or hydrogen hexachloroplatinate 2-. Okay, one more example. K3 AgS2 O3 2. So you may not be familiar with this ligand here. Do you know the name of this ligand?
Is that disulfite?
Yeah, so this is thiosulfate. Yeah, and as a ligand, it would be then called thiosulfato, of which we have 2. Okay, so now can anybody tell the entire name of the compound?
Would it be potassium dithiosulfato argentate?
Correct. That's correct. So you see that in this case, you need to use the Latin name for the metal, which goes along with the element symbol, which in this case argentum, but remove the ending um and place the ending ate directly behind argent. That makes it an argentate. Okay. Now, again, in the stock system, we would place the oxidation number in Roman numerals. So the oxidation number is in this case +1. Why is that so? Because the 2 thiosulfato ligands would have, well, 2- charge each, so that gives 4- charges, okay? 4 negative charges. But the complex has overall a 3 negative charge, which is understandable from the fact that we need 3 potassium ions to compensate the charge. So therefore, -4 + 1 is what gives -3, and therefore the oxidation number is +1. In the Ewing-Bassett system, we would place 3- in parentheses behind the name because the complex anion has 3 negative charge. Okay, now let us move over to the complex cations. The nomenclature of complex cations is similar. Firstly, to number and name the ligands. Secondly, you determine the name of the metal. Okay. And you then place either the oxidation number or the charge in brackets or in parentheses, depending on whether you use the stock system or the Ewing-Bassett system. That names the complex cation, and after that you name the counter anion, whereby again you do not count the number of the counter anions that are there. So when we name complex cations, we always use English names. We never use Latin names of metals. I don't know why it is that way, but it is that way, and we have to just follow what is customary. All right. So here's an example. We have AgNH3 plus Cl minus. How would we name this coordination compound? Realize first, well, we have a complex cation in this case. So we number and name the ligands. So we have 2 amine ligands in this case. Note that when ammonia acts as a ligand, it's called amine, whereby amine is spelled with 2 M's because ammonia is spelled with 2 M's. Okay, so when you name the ligand, spell it with 2 M's. Otherwise, again, you will lose points. Okay, so we have 2 of these ligands. Therefore, we have the name starts with diamine. So next we name the metal. So the metal name is now silver. We use the English name in this case. So it's a diamine silver. Now again, we need to determine the oxidation number in the stock systems. So the oxidation number is +1. Why is that? Because the amine ligands are neutral ligands. The complex has a 1+ charge, so therefore silver must have an oxidation number of +1. Or we place the charge in brackets. In this case, we would have a 1+ in parentheses. After that, we name the counter anion, which in this case, just chloride. All right, so what would be the name? It would be either diamine silver 1 chloride, or it would be diamine silver 1+ chloride. Both is possible. All right, just a few exercises here as well. So we have here a PTNH3,4Cl2. So what would be the name of this? We have printed out the lecture notes in advance. Try not to look at them.
Is it tetraamine platinum 2 chloride?
Correct. So we have 4 amine ligands. Our name starts with tetraamine. Then we name the metal, which is platinum. And then the oxidation state is +2, because again, the amine ligands are neutral. Our complex cation must have a 2+ charge because we have 2 chloride So the name is tetraamine, platinum 2 chloride, or tetraamine platinum 2 plus chloride. Okay, next example, NiH2O6Cl2. Anybody tell me the name?
Is it water nickel 2 chloride?
Yeah, almost. So now we have to remember that the water molecule as a ligand is called an aqua ligand. Okay. So know that. Then it is a hexa aqua. Okay. The metal is a nickel. So it's a hexa aqua nickel. And yes, the oxidation state is +2 because also the water molecules are neutral ligands. So we need 2 chloride anions to compensate the charge at the complex cation, which therefore must be 2+, therefore the nickel must be 2+. So it's either hexa aqua nickel 2 chloride or hexa aqua nickel 2+ chloride. Okay, now there can of course be cases in which we have coordination compounds that are made of a complex cation and a complex anion. So in this case, the same rules apply, just that we name the complex cation first and the complex anion last. So what would be the name of this then? So we encountered both the complex cation and the complex anion before. So therefore, this would be a diamine silver 1, hexacyanoferrate 3, or a diamine silver 1 plus hexacyanoferrate 3 minus. Note again, we do not count the number of complex cations or the number of complex anions that we have. Okay, now we can also have several different ligands coordinating to a metal. In this case, we name the ligands in alphabetical order. Okay. Note here that the name of the ligand counts, not the name of the prefix. So here's one example for that. So here we have a complex cation in which 4 amine ligands and 2 chloroligands bind to cobalt, and then that complex cation is charge counterbalanced by nitrate anions. So what would be the name? So we have to realize here that, well, amine comes first in the alphabet because A comes before C in the alphabet. So we therefore need to count the number of amine ligands first, which are 4. So therefore the name starts with tetraamine. Okay. Then we have 2 chloroligands. So the name continues with di. Chloro, because the ligand is anionic, gets the ending O. And then we continue with the name of the metal, which is cobalt. Then we still need to say what the oxidation number is. So in this case, we have a 1+ charge here at the complex because the nitrate anion has a 1- charge. You have to consider now that we have 2 negatively charged ligands, 2 chloroligands, 2 neutral ligands. So therefore we have to ask, well, -2 plus what gives +1? Okay, and the answer is +3. Okay, -2 + 3 gives +1, and therefore the cobalt has the oxidation number +3. So this would be a tetraamine dichlorocobalt 3 nitrate, or it would be tetraamine dichlorocobalt 1+ nitrate. Actually, this is a mistake here. That has to be a 1+ and not a 2+, because the nitrate anion has only one negative charge. Okay. Let's do one more example, and maybe this example you can do again. So this is PT NH3 BrCl H2O sulfate. Can anybody tell me the name?
Is it amine equal bromo chloro platinum 2 sulfite?
Can you name the ligands again? I'm not sure if I quite heard you.
Okay, amine equal bromo chloro
Yeah.
platinum 2 sulfite.
Yeah, that's correct. So the amine is first, then is the aqua, because M is earlier than Q in the alphabet. Then we have bromochloro. You have the platinum. The platinum has the oxidation number. Wait a sec. You said 2 sulfate or 4 sulfate?
1 sulfate.
One,
2. I'm sorry, 2.
2. Okay, let me just double check on that. So we have these neutral ligands, we have these negatively charged ligands, so that gives -2, right? So -2 plus what gives actually +2, because we have a 2+ cation here, because sulfate has a 2- negative charge. So -2 plus what gives +2? Well, that's +4, right? So therefore, the oxidation number of platinum is 4. All right. So it's an amine aqua bromo chloro platinum 4 sulfate, or it's an amine aqua bromo chloro platinum 2+ sulfate. I don't know which system you wanted to use, the stock system or the Ewing-Bassett system. But if you use the stock system, it's a 4, and if it's the Ewing-Bassett system, it's a 2+. Agree with me?
Yep.
Okay, good. All right, there's one more thing. Sometimes we have a ligand which is a more complex ligand, and not a simple anion and not a simple molecule. And more complex ligands occur, especially when we have not a monodentate ligand, but a multidentate ligand to consider. So in this case, in order to clearly say, well, what belongs to that more complicated ligand, we just place parentheses behind that more complicated ligand. Okay, and then when we number that more complicated ligand, we use slightly modified prefixes. So we use bis instead of di, we use tris instead of tri, we use tetrakis instead of tetra, and pentakis instead of penta, and so forth. So here's an example in which, well, this cobalt here binds to 2 terminal chloroligands and to 2 bidentate ethylene diamine ligands. So what would be the name of this? So first we need to realize that the chloroligands come first in the alphabet before the ethylene diamine. So the name would start out with dichloro. And then we would number the 2 ethylene diamine ligands. So the name would continue with bis, and then ethylene diamine placed in parentheses, and then cobalt. And then the oxidation number of the cobalt would in this case be +3, again, because these ethylene diamine ligands are neutral. These chloroligands have a 2 negative charge, and we have to arrive at a 1 plus positive charge for the complex cation in this case. So this would be a dichloro bis. Ethylene diamine, cobalt 3. If you use the Ewing-Bassett system, it would be a dichloro bis ethylene diamine cobalt 1 plus cation. Okay, now one more thing. We cannot only have terminal ligands, we can also have ligands that bridge 2 metal centers. And that is indicated in the nomenclature by a prefix mu before the ligand that bridges 2 metal atoms. So generally, we name bridging ligands first before terminal ligands regardless the alphabet, right? So bridging or not trumps alphabetic order. And then fragments with terminal ligands are named after that, after the bridging ligands, and placed in parentheses. So here's one example. So here we have a complex cation with 2 cobalts that are now bridged by these 2 ligands here. So this ligand here, an NH2 ligand, is called an amido ligand. Okay. So remember that, and don't call this an amino ligand. So in organic chemistry, we call an NH2 group an amino group. In coordination chemistry, we call an NH2 ligand an amido ligand. So remember this. And this ligand here, well, that's an hydroxyl ligand. So these are bridging, and then we have, well, terminal NH3 ligands placed around the cobalts in addition. So what would be the name? Well, we have to name the 2 bridging ligands first. Now we have 2 different ones, so we have to name them according to alphabetic order. So amido comes before hydroxyl, so we have a mu amido, mu hydroxyl, and then we have to name the 2 fragments that are bridged. So now we have 2 that are identical, and we place them in parentheses, and we place again the correct prefix. And because these fragments are more complex, we again use the prefix bis instead of the prefix di to indicate that there are 2. So therefore, the overall name would be mu amido, mu hydroxyl, bis. Okay. Now tetraamine cobalt, and the oxidation number of the cobalt would be 3 in this case. How do you determine this? Well, you need to realize that this amido ligand is anionic. This hydroxyl ligand is also anionic. So these two ligands have negative charges. So these other amine ligands here, they have neutral charge. And the overall complex cation has 4+ charge. So now -2 plus what gives +4? Well, -2 plus 6 gives +4. Okay, but now you have to distribute these 6 positive charges over 2 cobalt atoms. And that gives each cobalt formally a 3+ charge. And that means that the oxidation number of each cobalt is 3. So this is how you arrive at this Roman numeral 3 in the Ewing-Bassett system. Well, you can just read the positive charge at the complex cation, which is 4+. Okay, so this is what I wanted to say about the nomenclature of coordination compounds. So in the next step, we can now move over to coordination numbers and structures of coordination compounds, which are important, well, feature of coordination compounds. So first of all, let's talk about what is the coordination number. What's the definition of it? Well, the coordination number tells what is the number of points of attachments between the ligand and the metal. So now there can be different structures for different coordination numbers. And there are a number of factors that determine the coordination numbers and then the structures for each coordination numbers. So first, let us look what are the main factors determining the coordination number of a complex. So some of these factors have to do with the metal and some have to do with the ligands. So can you think about factors associated with the metal ion itself, which may determine the coordination number of a complex? Ideas? No ideas.
Is it the stability of the central metal ion? I mean, I remember some rules called 18 electron rules or something about the stability.
That's right. So the 18 electron rule, and we will discuss this later, determines the stability of a coordination compound. So yeah, that's correct. And the number of ligands a complex likes determines on that rule, because the more ligands you have, the more electrons you have. And the ligand chooses the number of ligands that leads to 18 valence electrons. That's right. Please don't write on my screen. So, well, the atom or the ionic radius will certainly play a role, right? The larger the ion is, the more ligands you can place around the ion. Okay, so that's a factor. But then there's also the electron configuration of the transition metal ion. So we'll see that different ion configurations prefer different coordination numbers. Again, that has partly to do with the 18 electron rule. So pertaining the ligands, well, of course, then the shape of the size of the ligands will be important. As I said, the size of the metal ion, the electron configuration of the metal ion. Lastly, also intermolecular interactions. So you can have actually different coordination numbers and structures in solution versus solid state. And that's then because when you have a coordination compound in solid state, the molecules start interacting with each other, while when they are in solution, they are far apart from each other and you don't have these interactions. So that can also have a different, it can also have an effect on the coordination number and the structure. So the next step, let us go stepwise through the different coordination numbers. We have low coordination numbers. These are the coordination numbers 1, 2, 3. We have, these are fairly rare. We have intermediate coordination numbers 4, 5, 6. So these are most common. Anything larger than 6 is then increasingly uncommon. But I think there's not enough time really to go over this. So I think we can actually stop here at this point and begin with the actual coordination numbers then in the next class. So we can just stop the